that is the one and only roller coaster song I know. It's by Red Hot Chili Peppers, in case you were wondering. Anyway, this video is going to be an opportunity to begin our discussions on how we will be collecting data to analyze roller coaster at Great America. And our first step is going to be using some of the basic equations and concepts that we've been developing over the year in order to go and calculate the speed of our train, of our roller coaster, at the top of the hill. So using those equations and using the data collection techniques that we're going to describe, you'll be able to be on your way to beginning our analysis of our roller coasters. Have fun! This is the first of 3 modules that we'll be doing using Blackboard. And like I said before, you're going to be using this particular module to find speed calculations. So calculating speed. So think about what we know about how fast things move and how we calculate that. And that will be our step to make this happen, to be able to understand how we can go and use that to be able to begin our analysis. Now, before we jump right into looking at finding that speed or velocity, I want to take a step back and look at what's happening on a roller coaster. So, I want to watch a roller coaster clip. And as we're watching this, I want you to think physics. So, as we're doing it, as I say to my students, talk physics to me. So, go through think physics, speak physics, what's happening as this roller coaster is going along the track. Okay, you're getting pulled up the roller coaster. The roller coaster is applying a force, causing you to move. So in other words, the roller coaster is doing work on you. As the roller coaster does work on you, you are moving up higher and higher and higher, which means you're getting more and gaining more potential energy. More potential, more potential. And at the way top, right about here, you now have the most amount of potential energy. When you have all this potential energy now, because the roller coaster did work on you, we now are going to experience this transition and transfer of energy. All this potential at top is now being converted into kinetic energy. And what we see is the transfer of potential into kinetic, etc., etc. Now, as we talked about in our last set, whenever we go over and we have roller coasters or we have anything that is moving in this kind of way, we know that we are going to have total energy as being the same, conserved. So this is an idea of conservation of energy. So we know that as we're moving on our roller coaster, as our potential is going down and our kinetic goes up, our energy, though, our total energy is staying the same. So we're going to go through and analyze how this type of roller coaster can really demonstrate all these great physics concepts. Now, as we're going through this, I want to take a little look at what's happening with our roller coaster throughout this experience, and specifically where our velocity, etc., is going to be highest and smallest. So here's my rendition of a roller coaster. We have our little train, which each of the little cars on the roller coaster heading up, and what we know are a couple different things. We know, as I said while watching the clip, we know that our roller coaster is doing work on this train, applying a force, getting it to move, and causing potential energy to be increasing and changing. We also know some other things about this. We also know here the way top, at the top, my potential energy is highest. And when my potential energy is highest, we also know that my kinetic energy is going to be lowest. In other words, when my kinetic energy is lowest, it means also that my velocity is going to be lowest at that top point. So we also know that at the lowest point, which I guess would be over here on this roller coaster, at the lowest point, it means my elevation or potential energy is going to be smallest. It also means that my velocity is going to be highest. So the main focus throughout this entire module set to prepare us for Great America is going to be looking at this idea, conservation of energy. our total mechanical energy is going to be conserved. We're going to look at kinetic energy plus potential energy that is equal to that total. We are going to, as we do these calculations, we're going to ignore the impact of friction and air resistance, and we're just going to look at those two forms of energy. Now, in order to calculate and determine those values, we're going to need to do some data collection. So we know we're looking at, first of all, this idea of total energy. So let's see what we need to know in order to be able to go and calculate these values. My kinetic energy, we know, is 1/2 mv squared. And my potential energy is mgy. So we know we're going to be having to go through and determine our mass. So that's going to be something we'll need to know before. We also know that we're going to have to use gravity, obviously. So really the two variables we're going to have to actually collect for at Great America will be the velocity and also the y, the vertical position. That will allow us to know the total energy of our roller coaster and of that system as it's moving. So we're going to start today by looking at our velocity piece, and then tomorrow we're going to talk about our position. Now, in order to figure out our total energy here, we're going to want to pick a point where it's going to be easiest for us to determine that value. And for our roller coaster, the easiest point for us is going to be up at the top. Up at the top, we know that our kinetic energy is lowest, so my velocity is smallest. And we'll also be able to calculate then, relatively easily, calculate that height so that we can find our potential energy. So the key in all of this is we want to figure out our velocity, our v at the top. So that's the entire purpose of this particular module, is figure out how do we calculate that velocity. Now, speed and velocity. Let's see if we can start with that piece. If we know we want to calculate the speed, let's see if we can think about our equation that we've used for this. Equation for velocity in particular. So think about it. V is equal to delta x over delta t. Change in position over change in time. In other words, when we talk about this change in position, we're really looking at that as being a distance traveled, if we're looking at our speed here. So distance over time would be a relatively equivalent way of looking at this equation. And we know that if we're doing that, we need to figure out a way of being able to calculate the speed for our roller coaster. So let's think strategies. How are we going to be able to figure out that speed? Well, we could get a radar gun or something like that, and try to see if we can climb up to the top of the roller coaster and figure out our speed. But that's going to be a little challenging. So is there a way that we'd be able to calculate the speed without having any fancy devices, using just this equation? So the first way in kind of looking at analyzing this is figuring out what do we know or could we find easily the length of? So let's think, if we have a roller coaster moving, what could we find the length of? Well, that's the real length, the easiest part and the easiest way for us to figure out a length would be finding the length of the train, of the roller coaster train. And you can find that length when you first walk in through the gates and you're getting ready to board the train and board the roller coaster. You can go and find a way to measure the train. But we'll talk more about what that's going to look like later on too. But if you know that, then you now know the length or the distance of the train. Time. What's time going to be, and how is that going to be relevant to this equation? So if we know we have a roller coaster moving, and we want to find how fast it's moving at the top highest point, we're going to want to figure out how long does it take for that roller coaster to pass by that highest point, knowing that it's pretty much traveling at a pretty constant speed at the top. This will make more sense in a second when we start watching the videos. But the idea is that time is the time it takes for the train to pass the highest point. So, as a result, we'll know the length of the train, the distance, and how long it took for it to move there, and thus we'll be able to find our velocity. Now, once again, I just want to revisit this again. When it comes to units here, if we're talking about velocity units. So looking at our V units, our velocity units, we're knowing that we know that we're working in metric units, so it should be meters per second. Meters per second. So now we're going to go and try to see if we can figure out how to calculate the length of the train. So in order to do that, I have students that are pretending that they are in a roller coaster. So use your imagination and imagine them as being rows in the train. And here's the explanation. The train. And the way to do that is to go and figure out a known length, which is your wingspan. So walk over to the rows in between the two people and figure out how far apart it is. How far apart do you think you guys are? Yay! A meter, in case you're wondering, is this. Make sure you think about this as being a meter. So they are 1 meter apart. Now we want to figure out how far is it going to be from all the way at the far end, the far row, up to the first row. So we have how many different separations or gaps between the rows? 1, 2, 3, 4. Conveniently, we have 5 rows. So to do this, you go 5 minus 1. So 4 gaps times 1 meter. So how far and what's the length of the train? 4 meters. So expanding on that, the idea is that when you have a length of a train, and the length of the train is going to be measured from the person who's in the first row over to the last row. And when we do this, we need to figure out how far apart our rows are. And that separation in this case for us, we found to have that as 1 meter. So what you're going to do is when you're going over to Great America, you're literally going to figure out what is the spacing between the rows on your given roller coaster. So in this situation, I have a total of 5 rows. And I have 1 meter between each row. So if we want to find the length of the train, that value, that delta x value, is going to be the number of rows minus 1 times the distance between each row. So as we said when we were going through this problem together in the video, what we got in this particular example is that the length of my train is going to be equal to 5, the number of rows, right? 1, 2, 3, 4, 5 rows, minus 1. And we found the separation between those values to be 1 meter. So the separation between the rows is 1 meter. As a result, what we'll get here is 4 times 1, or 4 meters in length. Now the other piece of finding the speed is to be able to calculate the time. So what we're getting here is that we want to find the time it takes for our train to pass by the given point at the top. In other words, when that length that we just calculated is moving, how long does it take for that length to pass by a point at the top of your roller coaster? So just going through this process again, this is our equation. The length of the train over the time it takes for that train to pass by that top point. So we found our length to be associated with this equation, the length of the train. And now we want to find this bottom point, the time it takes for the train to pass that point. So here's a video to help define that value and how we can figure out that value. And now we want to figure out how long it takes for the train to pass by the top point. So let's kind of do a mimic here of what this would look like. This is going to be the top point. So we want to figure out, with our stopwatches, how long it's going to take for that entire train to move past this point. So, and go! All right, ready? Your stopwatch is ready. And start. And stop. It took 5.54 seconds. So from there, we can do calculations and figure out how fast our train was moving. Thank you. Woo! So 5.54 seconds. Now, the other piece to remember is that you want to start your stopwatch as soon as the first row passes that top point and stop it when the last row passes by that point. So what we want to go through now is an example. If we know that our velocity is going to be equal to the 4 meters that we found at the top, divided by the 5.45 seconds that it took for that train to pass by. If I use my calculator and I plug that in, I get 4 divided by 5.54, and I get my velocity to be 0.72 meters per second. So once again, the same kind of stuff we talked about before, change in position or length over time, and just using that now with our own data collection to be able to figure out that velocity. Okay, so on the day of Great America, you're going to get a little data collection note card that's going to look like this. It's going to be for your group. So for your group of individuals, you're going to go and figure out your own personal mass and height and a couple other things. But really, the real piece that we're going to be collecting while we're there is going to involve this portion of our little note card. Now, like we said, in order to find the total energy, we want to find our speed, our velocity at the top, in order to figure out our kinetic energy at the top. So we're going to want to use these two sections to go and find that velocity. As we said, we're going to want to find our delta x, our displacement. And as a result, that length of the train is how we're going to get that. So on this portion of our note card, it says it's going to have information on collecting, how to collect data for finding the length of the train. And then up here, you're going to have information for finding the time it takes for that particular train to pass by the highest point. So those are the two pieces that you'll be using to calculate your initial velocity, which will subsequently be used to calculate our initial kinetic energy.